everyone, and welcome back to the Platypus Theatre at PyConline 2021. Next up, we've got Alan Green, who's going to give a talk on CFU Playground. He's a software engineer on the Chrome OS platform team, and in his spare time, Alan likes to play with oscilloscopes and do soldering. Take it away.
Thank you, Caitlin. Good afternoon. I am coming to you today from Lewisham, perched on the side of a leafy hill in Sydney's inner west. I'd like to acknowledge the traditional custodians of this land, the Wongal people of the Eora Nation. I'd also like to acknowledge the traditional custodians of the various lands from which we meet today and pay my respects to our elders, past and present. I am thoroughly excited to present the CFU Playground. The CFU Playground is an environment for building FPGA-based machine learning accelerators that are fast, low power, and open source. Python is key to making it all work and making it fun. Myself, my co-author Tim Callahan, and a number of others have been building the CFU Playground for the past year or so. The CFU Playground uses FPGAs to run ML models. ML here is machine learning, and an FPGA is a field programmable gate array, which you can think of as hardware, but with software-defined configuration. We'll examine what machine learning is and how machine learning models are run, specifically in the context of small computers. Then look at FPGAs and how they can accelerate arithmetic. We'll also see how to program them with Python. Next up, we'll take a high-level overview of RISC-V CPUs and how we extend them with custom function units. And finally, we'll tie it all back together with an example of accelerating ML on FPGAs. We're covering a lot of ground in a short time. I've tried to pitch this talk so that anyone with a little Python programming experience will get something out of it. But if you find yourself lost at any point, don't worry, there will be a new topic coming along in just a minute. Let's get started. Running machine learning models on FPGAs, especially on small FPGAs, is a little unusual. Here's how we got here. We had a project where it was necessary to be able to run ML models at low power, quickly, and using a completely open source stack. Now, open and fast together is straightforward. There are a number of well-supported open source libraries that can run on a PC or a phone class CPU. However, these CPUs were too power hungry for our application. Since CPUs are too large, we looked at microcontrollers with embedded digital signal processors, or DSPs. Many of these could meet our power budget, but, disappointingly, all the ones we were able to find had some kind of closed source component, a secret C++ compiler, a model preprocessor, or a blob to link against, so they weren't suitable. And while a microcontroller without a DSP can be low power and open, it can't also, at the same time, be fast enough. So we thought we might build our own ML engine out of an FPGA. My co-author, Tim Callahan, suggested using something called custom function units as a way to reduce complexity. The idea here is that we would implement our own low-power microcontroller-like design and then add custom function units to make the ML evaluation fast, while doing all this with a completely open-source toolchain. Once we decided that we wanted to build our own ML accelerators with custom function units, it became obvious that we needed some way to experiment with these CFUs. And this is how the CFU Playground came about. So the CFU Playground lets programmers build ML accelerators that are fast, low power, and open source on FPGAs and, as a bonus, in Python. The CFU Playground runs on real hardware. Here's one next to me for scale. This is one kind of FPGA development board we use, the Digilent RT-A7. We use this because it is reasonably obtainable, quite capable, and has an open source toolchain. There is also a USB port to communicate with the host computer. But what goes on the FPGA? When we start, the FPGA is a blank slate. We need to configure it. We know we need a CPU, so we define one of those. The CPU needs some memory, so we have some memory too. To communicate with the host, we add a serial peripheral port. And of course, there needs to be a bus to allow everything to communicate. The CPU runs TensorFlow Lite for microcontrollers, Google's open source library for ML on small systems. Now, at this point, the FPGA is a standard microcontroller, so it can run TensorFlow just fine, albeit too slowly for our purposes. However, we can now define a custom function unit that the CPU can use to accelerate ML models. As we'll see, we write the custom function unit in Python with nMigen. The exact kind of CFU we build will depend largely on the model we want to accelerate. Did I mention open source? From this list, I'll call out nMigen, the Python framework we use to write the custom function units, and another Python framework, LiteX, which we use to configure the system on chip, including CPU, buses, peripherals, and memory. Using this stack, the only thing that needs to be proprietary is the FPGA. So that's an overview of the CFU Playground and why it exists. Next, we're going to look at machine learning models. Machine learning has two important phases: training, which makes a model, and running, which uses the model. Let's look at training first. In training, one takes a bunch of labeled examples, which is a fancy way of saying, when you see this example, then give the label as an answer. And you give it examples for all the different kinds of output you expect. For something like image recognition, you'd need many labeled examples. The more the better. Eventually, after a lot of computation, maybe hundreds or thousands of hours, we have a model that knows it's hot dogs. We can then take this model and use it. The first step in running a model is to get some input data and then run the model with that input data to produce a result. But what does it mean to run a model? How does it actually work? Well, the model specifies a series of operations. To run the model, we set the input data, then run each of the operations one after the other to get a result. So, data in, operations, result out. Easy. An important type of operation is 2D convolution. The Illustrator model has two of them. Let's look at the TensorFlow source code and see how these 2D convolutions work. The code is in C++. It's about 30 lines. It will look complicated at first, but in less than 2 minutes you will understand everything we need to know about this code. The first thing to notice are the 7 levels deep nested loops, which we can illustrate with a friendly rainbow. Let's focus on the innermost loop, since that is where the code spends almost all of its time. The inner loop does 3 things. It fetches something called input from memory, then fetches something called filter, then it performs a simple calculation. It adds an offset to the input, multiplies by the filter, then adds the result to an accumulator. That's the most important thing. The code spends a lot of time multiplying and adding. To understand the rest of the code, let's take a look at the accumulator. It's reset here before the inner loop. Then after the loop, there's some complicated processing to compress the value from a large 32-bit number to 8 bits. And finally, the output data is stored in the output data array. The rest of the code is concerned with making sure that we get the right indices into the input data, filter data, and output data arrays at the right time. The most important thing to learn from this is that an ML evaluation is mostly a matter of running this one-line calculation millions of times with the right inputs. That was our whirlwind tour of machine learning, 2D convolutions, and the multiply-accumulate operation. Next section, we'll look at FPGAs and how they're configured. Now, before this presentation, many of you probably already knew that FPGAs are silicon chips, and the acronym FPGA stands for Field Programmable Gate Array. Array of gates means there are many programmable digital logic building blocks, and field programmable means that the logic blocks can be configured outside the factory. FPGAs are relatively slow by hardware standards, but incredibly fast by software standards. In the CFU Playground, we build up the FPGA configuration or gateware in Python with the nMigen library. But you could also choose to use Verilog, though that is not Python. The FPGA contains many different kinds of logic building blocks. Here are three that are important for us: the lookup table or LUT, the flip-flop, and the multiplier. The lookup table can be programmed to calculate any function that has up to 4 1-bit inputs and 1 1-bit output. For example, if we program it to always output 0 unless all 4 inputs are 1, then we have an AND function. And likewise, if it is programmed to always output 1 unless all inputs are 0, then we have an OR function. Arbitrarily complex functions of 4 bits can be programmed. With multiple LUTs, we can construct functions over a large number of bits, such as addition. LUTs function continuously. Any change to the inputs will be reflected at the output after just a few nanoseconds. With many LUTs, the delays can be quite complicated and hard to work with, so to synchronize the outputs of LUTs, we use flip-flops. The flip-flop's job is to remember a single bit. If it is enabled, it takes its input and sends it to the output on the next clock cycle. If it is not enabled, it ignores its input and keeps showing the same output value. A single bit can be useful, but to store multi-bit numbers, we can gang flip-flops together into registers. And finally, the third kind of logic block we mentioned is the multiplier. It does exactly what you would expect. It multiplies numbers. The question is, given a large number of these types of logical building blocks, how would we use them to implement a simple function that did an addition and a multiplication? The picture on the right shows one way to do it with LUTs and multipliers. A and B are two 8-bit inputs. A is added to a constant offset, then that and B are multiplied together to give the result. The adders would be made out of lookup tables, and we use the hardware multiplier block because multiplication is a more complicated function, and we may as well use the hardware we have. We'd express this configuration in the nMigen DSL like this. So the mul function begins by creating a 16-bit number object and assigning it to R. The m.d.comb plus equals notation means to generate gateware in the combinatorial domain, meaning that it happens continuously without flip-flops to synchronize signals. Its value is set by adding A to the offset and multiplying by B. Let's make a bit more room for our Python code here, because our next step is to have 4 add multipliers. FPGAs are great at having many copies of the same logic all running at the same time. Fortunately, our configuration language, Python, is also great at making many copies of the same object. In the design on the right, we have inputs capital A and capital B, which are 32 bits each. We slice up these 32-bit inputs into 4 8-bit values. Then for each of these 4 slices, we perform the same addition or multiplication, and finally add everything together to get a single result number. Looking at the Python code on the left, we still have our mul function from the previous slide, but we've added a new function which we've named mul4 because it does 4 muls. Mul4 uses a generator expression to slice the 32-bit inputs and do 1 mul for each of the 4 slices. It then uses the built-in Python sum function to specify that the results be added together. Looking at this point, we think it might be convenient to add the result of mul4 to an accumulator. The accumulator needs to hold its state, so we'd use flip-flops to make a register. And we'd connect it as shown on the right so that the result of the mul4 is added to the existing value of the accumulator. To do this in nMigen, we declare a 32-bit value named ACK for accumulator and use m.d.sync to specify that it is updated synchronously, meaning on each clock cycle. The value for ACK on the next clock cycle will be whatever value ACK has now, plus the result of the mul4. That's quite a bit, but I hope you see that nMigen is a relatively friendly way for Python programmers to specify FPGA configuration. Back to our outline, we are going to move on from FPGAs and arithmetic to how a RISC-V processor can be extended with custom function units. Here is the CFU Playground architecture diagram again. The bit we're interested in is the interface between the CPU and custom function unit. To illustrate how the interface works, we'll begin with a standard RISC-V add instruction. This is the assembler instruction in the form a programmer would use. As the comment helpfully points out, it adds register 4 to register 7 and puts the result into register 24. Of course, the CPU doesn't read the assembler instruction or the comment, it only understands the 32-bit instruction word. Let's look at those 32 bits. The first thing the RISC-V CPU looks at is the rightmost 7 bits, which form the opcode. In this case, 0110011 means this instruction is going to do something with the registers and the arithmetic logic unit, or ALU. The opcode also tells the CPU how it should interpret the remaining 25 bits of the 32-bit instruction word. The RS1 and RS2 fields specify which of the registers are sources, or inputs that need to be routed to the ALU. In this case, registers 7 and 4 are read from the register file. Funct7 and Funct3 are 10 bits in total that tell the ALU what operation to perform. In this case, they tell the ALU to add. RD specifies the destination register. In our example, the output of the ALU is sent to register 24. And that is the complete add. 2 values come from the register file, go to the ALU performs the calculation, and the result is placed back into the register file. Now let's look at how the custom function unit is used. The RISC-V instruction set has 2 reserved opcodes. We use one of those opcodes to tell the CPU to process data using the CFU. Once the CPU has seen the opcode, it understands how to interpret the remainder of the instruction. Just as with the add instruction, RS1 and RS2 specify the source registers, but the CPU routes them to the CFU instead of the ALU. Funct3 and Funct7 tell the CFU the operation to perform. And again, like add, RD specifies where the output of the CFU should be sent. So with this CFU instruction, a program can tell the RISC-V CPU to take 2 32-bit values from registers, send them to the CFU for processing, and put a 32-bit result back into a register. To allow the CFU to be used from a C program, the CFU Playground provides a CFU op macro, which GCC translates into a single CFU machine instruction. The example at the bottom of the slide shows C code and the assembler it is translated into. As you can see, the translation is pretty much one-to-one. So that was an overview of how a CFU works and how to use it from a C program. And now we're going to put it all together and accelerate TensorFlow Lite 2D convolutions. Here is our system on chip again. To accelerate 2D convolutions, we'll need to build a custom function unit that can assist with the 2D convolution, and then modify the TensorFlow implementation of 2D convolution to take advantage of the CFU. Here is the schematic for the gateway we defined 10 minutes ago. It needs a couple of tweaks to make it a useful CFU. First, having a fixed offset might work in some cases, but it's a little crude. We'll replace that with a register and some way to set the register's content. Second, this accumulator isn't really useful without a way to reset it to 0 at the start of every calculation, so we'll add that too. This is enough to be useful. Now, here's the nMigen code to implement all this. There is a little more boilerplate that surrounds this code, but I've omitted it in order to get this all into one slide. Here are the important parts. We begin by defining offset and ACK as 9 and 32-bit signed numbers. Next are our mul and mul4 functions. These work in the same way as we saw before. The next line sets a done signal the cycle after start is received. All the functions we perform take a single cycle, so this is fine. And this line ensures that the CFU always outputs the accumulator value. The nMigen DSL uses the with statement in an interesting way. The with m.if means whenever. So whenever self.start is true, then the contained logic is enabled, otherwise it's disabled. Whenever start is received and funct7 is 0, then the first input value, in0, will be set into the offset register. Alternatively, if funct7 is 1 while start is true, then the accumulator is reset to 0. And finally, if funct7 is 2 while start is true, then we perform the mul4 on our two input values and add it into the accumulator. And that's all the gateway we need. The Python nMigen syntax makes it pretty compact. So remember this code? We're going to use our new gateway to accelerate the inner loop. The first thing to note is some C++ pointer shenanigans. The original code retrieves 8-bit values, but for the CFU version we can process 4 8-bit values at a time. These shenanigans allow us to retrieve 32 bits at a time from the input data and filter data arrays. At the top of the file, we hash define a macro that wraps the CFU op macro, and then we use it here. These are the main changes, though we also need to set the offset and reset the accumulator at appropriate points. This table shows how the accelerator we just made works with one of the TensorFlow Lite for microcontrollers example models. The overall model evaluation time has shrunk from 147 million cycles to 85 million cycles, a 1.7 times speed up. If we look at the individual operation we were targeting, the 2D convolution, we've managed a 2.8 times speed up from 95 million cycles to 33 million cycles. Not bad for 20 lines of Python and another 15 or 20 lines of C++. In this talk, we looked at how tiny ML models run. They're doing millions of adds and multiplies. We also looked at what FPGAs are and how to build gateware that does those adds and multiplies. Then we looked at how a CPU interacts with the custom function unit. And finally, we put it all together to build an accelerator that makes running an ML model faster. There are plenty of aspects of the CFU Playground that we didn't cover. We've put a lot of effort into tutorials and guides for beginners. People who do them tell us they're helpful and fun, so please try them out and raise bugs to give feedback. Unit testing gateware in Python is fun. It's definitely more fun than debugging it on hardware. And I'm a bit sad that I didn't have time to talk about CFU Playground's iterative baby steps approach to building gateware that is definitely easier and therefore more fun than trying to build and integrate giant components. There are many people to thank for their part in making CFU Playground a reality. I would like to call out a couple. First, Tim Callahan has done the majority of work putting together the structure of the playground so the rest of us can have fun writing accelerators. I would also like to call out the work of our interns, Rachel and Joey. Both Rachel and Joey started off knowing very little about FPGAs and ended up implementing whole accelerators. Joey even wrote up a step-by-step guide for getting started, and I made heavy use of that guide in this talk. If you'd like to learn more about FPGAs or understanding the nitty-gritty of how ML models are evaluated, or building ML accelerators with open source tools, then here's how to get started. The tutorials and guides on cfuplayground.readthedocs.io is the best starting point. The code is all up on GitHub under an Apache license. And that's all I have today. I'll be able to answer questions now and for the rest of the afternoon, but also feel free to reach out to us from any of these channels. We're always excited to have people learning about FPGAs and machine learning.
Excellent. We do have some great questions, so we can get straight into them, I think.
Fantastic.
I'll go for the most tongue-in-cheek one first, which is, what are you building?
We're building a thing which may or may not work. If it works, it may appear in a Chromebook.
Great. Next up is there support for non-Altera / X-Linux FPGAs like Lattice or the interesting SciPed Chinese FPGAs, and also the Lattice targeting open source toolchain?
Yes. We really want our product to be open source, and so we're going out of our way to support open source toolchains wherever we can. The Lattice toolchain's great. The Xilinx toolchain's getting there. These are all good.
Excellent. Our next best up voted one was, as a person with curiosity but no real hardware knowledge, what's a good entry point into Edge ML or Tiny ML? Particular projects or references? Thanks for the beautiful explanations.
Yeah, the CFU Playground is a great way to get into it. The TensorFlow Lite for Microcontrollers site actually has pretty good instructions if you wanted to get started, and they recommend a number of microcontroller products. That is actually not a bad way to get into it. The CFU Playground, if you wanted to get hold of like an FPGA development board, we make it super easy to just get into it and start messing around with the C code.
And I think that some conferences give FPGA boards as like the particular badge for the conference, so they can all often be quite good.
If you have a development board or a conference badge that you'd like to see the CFU Playground on, please get in touch. That'd be fun.
You mentioned that we're using a reserved RSIC-V opcode. Is this space reserved for custom opcodes, or is it there for future use by standardized opcodes?
Good question. No, the RISC-V specification reserves these two opcodes for implementers. They're never going to be used for RISC-V instructions. There are other reserved spaces for RISC-V instructions, but these are specifically so that implementers like the CFU Playground can try out new things. It's one of the really great things about RISC-V is you have this giant RISC-V GCC toolchain that already works, and then you can add just a little bit that you need to make it better, to make it do what you want.
We've got one more question. If there are any more questions, you might have time to type them in before we get to them. Is it easy to write functional tests for components generated in MA? I'm going to fumble over every single acronym here.
nMigen? It rhymes with pigeon.
Do you
I had to ask.
the Python side of things? Oh no, yeah, you would have to. Or do you run it through hardware simulators?
We do both. So we definitely find the most bugs with Python unit tests. Python unit tests are import unit test and then subclass unit test.test case, and then nMigen has a simulator, and you can poke at the simulator and check that it's giving you the results back that you want. The test cases are really fun. I don't know of any other environment that lets you write some gateware and test it and fix it and run it again in less than 30 seconds.
That's pretty good. We've got a flip side, which is, if as a person with lots of hardware experience but no ML experience, where's a good starting point for that?
Ooh, I'd have to think about that. Please come and talk to me afterwards.
Yeah, that'll be a good thing. We've got the hallway track, of course, for that. And one last question from Miles is, why do you need 4 times mol times 8 rather than 1 mol times 38?
Right, good question. So this all comes down to the technology that your ML model is using. There's a lot of research being put into 8-bit models at the moment. And the good thing about 8-bit models is you can move the data around 4 times as fast because there's 4 times less of it. So that's why we're using 8-bit models.
That's nice. I think that's all we have for questions. Thank you so much for your talk, Alan. This was really good.
Thank you. Thank you to everybody.
Yeah, if you want to continue the conversation, we've got a long break coming on, so you can continue to use this hall or the whole text chat that's related to it. During the lunch break, if you've got some spare time, and you're interested in it, the Lightning Talk submissions close at 1 p.m. Australian Eastern Time, which is in half an hour. If you think you can come up with a 5-minute talk on any interesting topic, doesn't have to be Python related. Thank you, Mickey. My cat just meowed. Absolutely get that in. You can find the links in the social chat or in pycon.org.au/social, and that has links to all the social events happening over the next day. Yeah. Thank you so much.